So hi, this is our chipper project, and we got assigned the middle part of the chipper grinder. And I got this wood chipper slash shredder from my boss, and it hadn't ran in over 10 years when we got it. And it took quite a bit of work. We had to fix the recoil, we had to fix the coil pack, and we had to fix the carburetor and unseize the centrifugal clutch. And after all that, it got running well. And one thing that I couldn't repair because we couldn't get the part in time was the kill switch. So in order to kill it, you just have to ground this wire out right here because the switch was faulty. And it's also a 1991 model, so to order a switch was almost impossible. But next, we'll go into our modifications. And for input modification, we added this door right here. And we used polycarbonate so you can see through it, and it's also strong enough to resist wood chips and other things coming up and hitting against it. And then also adds increased safety. And then on the output, we added an extended chute to kind of keep the shavings or chippings more collected, and then also allows us to run it into a bag or a tube or the other team's machine or whatever have you. So first, to get it started, you want to put the gas at almost the lowest point, just barely turn the gas on a little bit, and then that's it. No choke or anything, and it starts the best. To show how fine it grinds it up, this was branches, leaves, and everything, and as you can see, it ground it up into a very fine dust, all of it.
So to start the shaft design, we took a look at all the components in the grinder, the shredder, and there is a flat belt pulley that's connected to the motor. That is what drives the shaft. There's bearing A right after the belt pulley. And then there are 3 blades followed by another bearing on the far right. So the flat belt pulley has the tension side is 105 pounds. The non-tight side is 40 pounds. And then to get the load on the shaft, the bending load, I had to get the force, normal force, and you take the tightened load minus the smaller load, and I got 65 pounds. Then for flat belt pulleys, you multiply that by 2 to get the bending load. From there, I went on to get the load on the actual shaft. So we got the pulley load right here, and that's going up. The pulley is providing 8 horsepower at 2,500 RPM. The blades, they all weigh roughly 15 pounds each, and those are laid out right here. At the top, you can see the measurements between each component. So the next thing I did was I calculated the torque, and to get the torque, you multiply 63,000 by the power, and then divide that by the RPM. So the torque through the shaft is 201.6 inch-pounds. And this torque does not change throughout the shaft because there is no output. There's nothing being driven off the shaft, it's just a spinning blade. I also chose the shaft to be SAE 1040 cold drawn steel. You can go down. So the next thing I did was I did a moment calculation to calculate the forces on the bearings. I found that the force on the bearing on the far right, the bearing F, was 64.4 pounds. From there, I was able to just sum forces and get the force in bearing B, which was 149.4 pounds. I then made a shear diagram which showed that the shear first goes up to 130, comes down to negative 19.4, goes down to negative 34.4, goes down to negative 49.4, finally goes down to negative 64.4 where it returns to 0. Then from there I was able to make a moment diagram. The moment diagram goes from A at 0 to at B 410.85 inch-pounds, then to 459.6 inch-pounds, then to 560.85 inch-pounds, then to 716.475 inch-pounds, and then all the way down to 0 at F. I then drew a layout of the shaft, mainly securing the bearings and the blades with slip rings, and that was my shaft calculation. And so I also wanted to say the reason I didn't, so these are all axial loads, all these calculations are for axial loads. There was no tangential loads in our shaft because there was no outputs and there was no forces from the sides. So these are all axial calculations. All right, so next I calculated the key for the motor to the pulley. I found that the motor outputs a max of 36,000 RPM, and the max torque, or the torque with that RPM is 11.7 foot-pounds. The power again is 8 horsepower. I wanted to design this for the max output so the key would experience the most force. The diameter of the shaft, of the output of the motor is 1 inch. I then converted the tension to inch-pounds, and I also gathered the width and height of the key. From there, I was able to calculate the length required of the key. The minimum length is 4 times the tension times the constant N, which I took as 3, divided by the diameter 1, divided by the width, and then again divided by the yield strength. I then got the minimum length required to be 0.1925 inches, which is not a standard size, so I rounded up to 1/4 inch. For the pulley design, I took the diameters of the 2 pulleys, which were 4 inches and 4 inches, and then I took C to be 8 inches max, the center distance, and I also calculated this for a 3V belt. The length is using this formula right here. The 2 diameters are the same, so this term cancels out. I then plugged in the numbers here and got a length required of the belt to be 28.56 inches. I then had to round this down to a normal length of 28 inches. Then I was able to calculate a B value, which is then used to calculate the center distance. So for the B value, I ended up getting 61.76. I then plugged that into the center distance calculation, and I was able to get a center distance of 7.72 inches. And also the wrap angles are both 180 because the pulleys are the same diameter. For the bolt design, we calculated the bolts on the door of we made the acrylic door for the lid of the shredder, and we calculated the bolts in the handle of that. So I took the bolts, I assumed the bolts were grade 1 because I knew there wouldn't be a lot of force on them. I also assumed that we would only be using 75% of the proof strength. I then took the clamping force to be 100 pounds. And then I took the load on the bolts with the door to be 100 pounds. So that's divided over 2 bolts to be 50 pounds per bolt. So I calculated the stress in the threads, or the max stress in the threads, as 75% of the yield strength, or of the proof strength. And I was able to get the proof strength I was using was 24,750. I then was able to calculate the area of the threads required, and this came out to a super small number, which was expected because we're dealing with super small loads. And this came out to 0.002 inches. The lowest size of bolt we have was 1/4 inch, so I just had to round up to a 1/4 inch. I know there's other ones, but that was what was in the book. I then was able to calculate the tightening torque, which is KDP. I took K to be 2 because I didn't think we'd be lubricating this. I took the diameter again to be 1/4 inch, and then I took the load on the bolts to be 100 pounds. And this came out to a tightening torque of 5 pounds per inch. And yes, this is super low, but these are also 1/4 inch bolts, and 1/4 inch bolts, especially grade 1 1/4 inch bolts, are known to strip. So this makes relative amount of sense for what we're doing.